Very good morning to all my dear students. Hope with the God grace you all are safe and fine. My dear student, as we all are aware that now offline school has been started, the students, those who are attending the offline school, it has a lots of beneficial effect if you are coming to school and if you are attending the lecture or class physically, because we are aware of more and more knowledge about our study. We will get the knowledge about our studies. At the same time we will be getting to know, or you can clarify your doubt at the same time. Now my dear student, let's begin with our 10th standard water security subject. My dear student, in the classroom I had already given you all the question answers of chapter number 1st and 2nd. Now we shall be moving towards the chapter number 3, measurement of water. In this particular chapter, first we will be understanding the meaning of water security. At the same time we will be understanding rainfall measurement, rain gauge, evaporation measurement and surface flow measurement. Hope you all will watch the video till end, and in the next class when I will come to the school I will be giving you all the question answers. Please complete the assignment, please complete the notes. As we all are aware that it's a grading subject, I had already instructed you all in the class, even in the video also I had instructed you all. So book completion is very important. See to it that each and every question answer you will write it in your assignment notebook whichever you have made for this subject. So let's watch the video till end.
The world will not be able to meet the great development challenges of the 21st century: human development, livable cities, climate change, food security, energy security, without improving how countries manage their water resources. Population growth, unsustainable economic development, pollution and mismanagement are pushing water resources in many parts of the world to their limits. Climate change ups that risk. It increases water demand, changes flow patterns, and increases the frequency of floods and droughts. There are 276 cross-national river basins in 148 countries, covering 40% of the world's population. States need to agree on joint water resources management if they are to share costs and benefits.
If water can give us life, then destroying the systems that deliver water, and indeed the systems that give stability to populations, can take life away from them.
Over 150 river and lake basins are shared by 2 or more of the OSCE's 57 participating states. Shared water resources can cause tensions and even conflicts, but they can also be a source of cooperation, trust, and security. This is where water diplomacy comes in. Finding solutions that balance the conflicting needs and interests of different countries and sectors. Jointly managing water can improve relations among countries and enhance security, prosperity, and the protection of the environment. This makes water an essential element of the OSCE's comprehensive approach to security.
Sustainable water management is key to ensuring peace, stability, and security. Although we are making progress in identifying and taking advantage of opportunities for water cooperation, much more needs to be done if we want to be serious about preventing conflict.
The OSCE supports countries in jointly managing water resources sustainably, particularly in the Sava, Dniester, Kura and Chutalas basins. Since 2004, the OSCE and its partners in the Environment and Security Initiative have backed negotiations on joint management of the Dniester River, culminating in an agreement between Ukraine and Moldova in 2012. The current water crisis is mainly a crisis of water governance. Good governance is essential to prevent water-related conflicts at every level, from local to international. It allows resources to be managed accountably, transparently and equitably, and to resolve disputes in a legitimate way. OSCE field operations promote good water governance through activities such as training courses on integrated water resources management, support to water user associations, and to water policy reforms. On the political level, the OSCE brings together policymakers, experts, private sector and civil society to discuss water-related issues. The 2015 Serbian OSCE chairmanship has even decided to devote the annual Economic and Environmental Forum to water governance. The OSCE is well placed to address water and security challenges. It brings together all concerned to discuss challenges, putting water high on the security and foreign policy agenda. On the ground, it carries out projects that bring security benefits through good water governance. It turns water from being a potential source of conflict into a tool for confidence building and cooperation. Learn more. www.osce.
This is rain gauge, simple rain gauge. Today I will tell how to collect rainfall data. This is a very simple rain gauge. It is having circular collecting area. This is collecting area. And inside there will be jar. Into this jar, rainfall will be collected. Daily we collect this water and we will measure the rainfall in centimeters and millimeters. First, we should know how to calculate the rainfall from this collected water. Here, we should calculate the surface area of this brim. Suppose I am measuring this diameter nearly 16 centimeters. Diameters of this collecting area is 16 centimeters. Then radius will be 8 centimeters. Then we calculate this surface area, collecting surface area. The formula is pi r square. Pi is equal to 22 by 7. R means here 8 centimeters. Pi r square means 22 by 7 into 8 into 8. You see, I will show in this paper. See, diameter of the exposed area of surface of rain gauge 16 centimeters. Now we have done. Radius 8 centimeters. Area of exposure to rainfall collection pi r square, that is equal to 22 by 7 into 8 into 8, that is equal to 201.14 centimeter scale, means square centimeters. Now rainfall in centimeter equal to collected rainwater divided by area of the exposure of this rain gauge. Area of the brim. Area of the brim is equal to 201.14 square centimeters. Now we will calculate. We collect the water. How much you will see? I am collecting this water. This is the water. I will pour in this measuring cylinder. This is 100, 150, nearly 155 ml we collected. Okay, we collected 155 ml. Now we calculate. Just now we calculate. Already we know surface area of this brim is 201.14 square centimeters. Collected water is how much? 155 ml. So collected water divided by surface 155 ml divided by 201.14 square centimeters, that is equal to 0.77 centimeters. Today rainfall 0.77 centimeters. If we multiply with 10, it will be converted into millimeters. Into 10 is equal to 7.7 mm rainfall. Today's rainfall is 7.7 mm. So in this way we should calculate the rainfall.
When I was a kid, I used to watch these weather reports that used to come on TV, and that person used to tell that Mumbai got 85 millimeter rain, or let's say Chennai got 75 millimeter rain. And I was always wondering, how are they measuring rain using this millimeter? And then later I came to know that they use this instrument or this tool called rain gauge. And what it does is basically it is a container whose opening is of the same size as its base and its sides are straight. So whenever I used to go to a library, I used to take these science experiment books, and they used to describe how can you make one rain gauge on your own. Take any container which has the same opening and the same base, and the side should be straight. But then I thought, can't I take a container which has a smaller opening, but the base is same as that opening and the sides are also straight? Can I take this container and measure the rain? So if I keep these both outside, let's say it is raining, and if I keep these boards outside on the ground, and I want you guys to think what will happen. Let me just draw this properly. Okay, so let's take so let's say I have one container which has a smaller opening, and I have kept these both out. It's raining and I've kept these both out. And I wonder now in which container will water get filled fast? So we know if the water is filled till here, then we need to measure this height, and let's say it is 50 millimeter. Then we say that it has rained 50 millimeter in this place. So my question is, when we have two different containers, will the water level be the same in these both containers, or the water level in this container is more? Just think about this for a second. So now let's try to find the answer for this. And in order to do that, let me just redraw this whole thing again in a different way. Okay, so in order to answer this question, whether this container has more water level or this container has more water level, or are they equal? So in order to answer that, so we can either do it mathematically, which I'm not going to do today, or we can try to just see it using diagrams. So I have just redrawn this whole thing, and what I have drawn is I have just represented this rain in a different way. So let's say that it's raining for just a small amount of time, and that rain, I have represented it as a layer like this. So imagine this whole layer, it is coming down, and if you're standing here, you will feel the rain for some time, and after some time it will just it will stop raining. So it is raining just for a small amount of time. In order to help you visualize, you can think of it like this. So this is the rain and it is coming down. It's coming down, it's falling down. You are standing here. So as soon as the rain touches you, you feel that, okay, it's raining. It is raining, it is still raining, and now it has stopped. So you can imagine the rain in this way. So if it is raining for a longer time, what I can do is the width of this will be much bigger if it is raining for a longer time. If it is raining for a much longer time, it will be much bigger. But so that's how I'm representing the rain. And one more assumption, and another thing that we have to assume that, these drops, right, they are distributed uniformly. If you take any particular area and if you count the drops in how many drops are there, so you will feel that we are assuming that the density of those drops or the number of drops in one particular area, it is the same all throughout. So that is another assumption that we are doing just to keep things simple. Okay, so let's try to understand this, answer this problem. The raindrops are falling down and it's coming down. Now you can feel that it has started raining. And now also try to observe what will happen when rain hits these containers. So as the rain passes down, as the rain goes down, and once it stops completely, what do you think will be the water level in these two containers? Just think. You can pause the video and try to answer this question. So because, the way I have drawn the diagram, it now, I don't know if things will be clear, but as you can see, the level of water in these two containers, it will be the same. We can try to visualize this and we can see that, as it rains below, this container, it will get filled with this much amount of water, right? Whatever is right above it. So it will get filled with this much amount of water. And this container will get filled with whatever is falling on top of this. Okay, so that is this much. And this container will get filled with the water which is on top of this. So this whole thing will get filled with this. This whole thing will get filled with this. So you can just visualize that. So it falls down, it comes, and after that it stops raining. So you can see that, the level of water, it will be the same in both these containers. So if the water level is this much, if it comes down, so the water level will be the same in both these containers. It is the same in both these containers. And if you, let's say I have a much bigger container. Let's say I have a much bigger container. Let me draw a little bit big. If I have a much bigger container, still this container will get filled with water which is falling on top of that, right? So this will get filled with whatever is on top of that. So again, the water level will be the same. So here we can see that the water level, the height of the water is the same in all three containers. But yes, this will contain less water. This will contain a little bit more water because the volume is higher. And this will contain the most amount of water because this has the highest volume. So the volume is different, but we are not interested in volume when we are measuring rain. We are only interested in height. So no matter what the size of the container, the height will be the same. Let's say if this is 50 millimeter, if this is 50 millimeter, this is also 50 millimeter, this is also 50 millimeter. So you can see that, you can say that, it has rained 50 millimeter in this area. So you can see the size or the diameter or the opening of this container does not matter. Only thing that matters is The opening area should be equal to the base and the side should be straight. And this is why the size does not matter, because the height of the water will be the same. And now something for you to think about. Now if I change this container with a container of a different shape, let's say this is cylindrical in structure. Let's say I don't use a cylinder, but I will use a cuboid shaped container. Now, what do you think will happen now? So this is something that you can think on your own. If you get the answer, please type in the comment section. That's all for today. Thank you for watching.
Subsurface flow, in hydrology, is the flow of water beneath Earth's surface as part of the water cycle. In the water cycle, when precipitation falls on the Earth's land, some of the water flows on the surface forming streams and rivers. The remaining water, through infiltration, penetrates the soil traveling underground, hydrating the Vadose zone soil, recharging aquifers, with the excess flowing in subsurface runoff. In hydrogeology it is measured by the groundwater flow equation. Water flows from areas where the water table is higher to areas where it is lower. This flow can be either surface runoff in rivers and streams, or subsurface runoff infiltrating rocks and soil. The amount of runoff reaching surface and groundwater can vary significantly, depending on rainfall, soil moisture, permeability, groundwater storage, evaporation, upstream use, and whether or not the ground is frozen. The movement of subsurface water is determined largely by the water gradient, type of substrate, and any barriers to flow. Subsurface water may return to the surface in groundwater flow, such as from a spring, seep, or a water well, or subsurface return to streams, rivers, and oceans. Water returns to the land surface at a lower elevation than where infiltration occurred, under the force of gravity or gravity-induced pressures. Groundwater tends to move slowly, and is replenished slowly, so it can remain in aquifers for thousands of years. Mainly, water flows through the ground which leads to the ocean, where the cycle begins again. Flow within the soil body may take place under unsaturated conditions, but faster subsurface flow is associated with localized